Our quick look at the calendar. Today we cover something called trig identities. That is in section 9.1. Thank you guys for finding my mistake. The reading from last night should have said read section 9.1, not 7.2 or whatever it said. So if you weren't able to do the question of the day, don't sweat it. Just turn something in saying you did the reading but couldn't find it. One other thing I want to talk about is the date of the project 7, the due date. It is due on class 29, which is Wednesday. This is accurate. On the top of the project itself, it says class 28. That's a mistake. So the project is due Wednesday, just like I had said. Did I say Wednesday in class? I said it, yeah, so it was a week. It is due Wednesday, but at the top of that project, it says 28. It should say 29. Any questions on any of that? Okay, and then the only other thing in the calendar coming up is on Monday, our 7th quiz, which will be on the sines and cosines stuff, as well as the trig identities that we're doing today. That's today. On the quiz, you may use the trig identities handout and the unit circle. And the unit circle. So is that the first page, Tassiday? Yes, you may bring that with you to the quiz. And the unit circle. All right, so we are here at the top of page 6, and we'll start with Vanessa with number 1. Okay, let's look at that equation. Is x squared equals 9 something that's true for all values of x? No, it's an equation. It's true for some values of x. What values of x make this true? 3, also -3. It's true sometimes, and it's an equation, and you can solve a lot of equations. But that's not what an identity is. An identity is something which is true all the time. Take a look at the other equation. X times x cubed equals x to the 4th. Is that true for every value of x? Yes, it is something which is true all the time. There's a fundamental difference between those two things. The first one's an equation that you might try to solve. The second one is an identity, something that's true for all values of x. We see the distinction? All right, so everything we're talking about today is going to be identities. We'll go to Hillary for right above 2. Okay, Chris? 2. Just above, number 2. Okay, so the first one, x plus 3 squared equals x squared plus 9. Is that like a law of algebra? Is it something that's true all the time? Seems reasonable. Is it true all the time? It's not. It's tempting. A lot of people think this is true. It isn't, but if you're not sure, then on a calculator we could either confirm or, well, I guess we can't confirm, but certainly we could deny. So if on the calculator I typed in x plus 3 squared, and then separately graphed x squared plus 9, if it's an identity, it should be exactly the same graph. I should see the same thing graphed twice. Did I? No. I see the one graph on the left, the other graph up on top. They are different. It's not an identity. In order to prove it's not an identity, all you need to do is pick one value of x that makes those things not equal. For example, x equals 2. I'm guessing those are not the same number when you plug in x equals 2 on both sides. How about the next equation here? Square root of x squared plus 9 equals x plus 3. Is that true? No, in fact, I feel like that's the same, that's just a restatement of the thing on the left. So you could graph the two of them and you'll see different things. All right, how about this beast? 1 over 1 plus cosine x plus 1 over 1 minus cosine x equals 2 cosecant squared x. Is that true? I have no idea. But the calculator can maybe give us a sense of whether or not it might be true. So this one requires some very careful typing. So let's carefully type this thing in. 1 over, note the parentheses, 1 plus cosine x, plus, and then we'll do the other fraction, And I don't have a cosecant squared. I don't have a cosecant button. How do I type cosecant on the calculator? 1 over sine. It's the only way to do it. So I'm going to type 2 times 1 over sine. Sine x squared. Where do we need parentheses? At the end? Yeah, you never need trailing parentheses. You can put them, and like technically it's wrong because it's missing a couple of parentheses, but calculator doesn't care about parentheses at the end. Okay, so cosecant squared is 1 over sine squared. I've typed that in there, and I think we're good. All right, so let's graph. I don't really know what to expect, so I'll just hit graph and see what it does. Okay, so there's some pieces. Kind of looks like a cosecant or a secant thing. We looked at those graphs briefly. All right, it's still doing stuff. I can see the little Knight Rider thing in the top right, but so what, is it true? Well, yeah, what would we expect to see if you graph the same thing twice? We wouldn't see anything the second time. So I don't have enough information. It's possible the whole time it was thinking and it looked like it wasn't doing anything, it was just redrawing this, which would be great. Isn't it also possible that the graph of the second thing is like off the screen? In which case I wouldn't see it. So how about we go down here and then scroll to the left, and you guys know if you highlight that little thing and hit enter, then you can change the way it looks. So this one at least, we should have a way to know if it's tracing over the first time, the first thing it drew. So all those cups are the left-hand side of my equation, and that right there is the right-hand side. Does this look like it might be an identity? Sure does. Is that proof that it's an identity? It's compelling, but it's not proof. Isn't it possible that these don't exactly land on the, I mean, like there's only pixels that I'm looking at. It might be close, but not perfect. Isn't it also possible that it looks perfect here in the middle, but if I were to just go a little bit further to the right on my viewing window, they would look very different? Okay, so we can never prove an identity by looking at the picture, but the picture can certainly give us a sense of whether or not something has any chance of being an identity. Let's try 3, Kyle. Okay, so which of these are identities? This one was a no. This one was a no. This one was maybe. Probably. Okay, so we're going to try to prove that this thing here in part C is true all the time. First thing I want to say, maybe the most important thing to say about identities, you cannot multiply both sides of this equation by, for example, 1 plus cosine x. That seems like a good thing to do because it gets rid of that fraction. You cannot multiply both sides by 1 plus cosine x because you don't have an equation to multiply both sides by. You have something with a big old question mark on it. It's not an equation. And at no point in the process that we're about to do are we allowed to cross over that line. You cannot do something to the left and the right because the left and the right at the moment are unrelated to each other. So don't do anything crossing over the equal sign. All you're allowed to do is play around with the thing on the left and hopefully transform it into the thing on the right. So we'll start there. I'm going to copy that thing on the left. Yes, Chris? What you said earlier about good question. Let's go to question 2 on the questions of the day. Is that here? Yeah. So this equation right here, it seems like what could we cancel from both sides? Sine of t, and you end up with cosine of t equals 1. I guess I should have said divide by 2 sine of t. But if you do that, you actually end up losing some solutions because, for example, let's see, cosine of t equals 1. That happens at 0 and then again at 2 pi. But if you plugged in, for example, t equals pi into both sides, anybody remember what the sine of pi is? It is 0. So the whole left-hand side is 0. And how much is the right-hand side when you plug in the pi there? also 0. So the equation is true when you plug in t equals pi, but you would never know it looking at the other version. And so crossing these things off is legal as long as sine of t is not one what bad number. It's not 0. You're not allowed to, like crossing them off is really division, right? You're dividing both sides by sine of t. So you're allowed to do that as long as sine of t is not 0. But it's so easy to miss that my recommendation whenever you have something like this is to bring everything over to one side. I like when equations are equal to 0. And then factor. Instead of divide, factor out. It's like division, but it's still there. And then I get to split it up and say either 2 sine of t is 0 or cosine of t minus 1 is 0. The right-hand side is exactly what we expected. Cosine of t equals 1. The left-hand side is the stuff that we divided by, but it still has solutions. So don't divide both sides, but rather bring everybody over and then factor. I don't think it's the same phenomenon. This is an equation. You're allowed to do the same thing to both sides. That's not an identity, but it's a good observation. And I'm glad we looked at this one. Okay, so let's come back to here. 1 over 1 plus cosine plus 1 over 1 minus cosine equals. Let's see, am I allowed to say equals to cosecant squared? No, I don't know that it's equal to that. I'm trying to prove that it's equal to that. All I'm going to do is manipulate that thing. Okay, you're adding two fractions. The natural thing to do is to find the what? The common denominator. Let's do that. What is the lowest common denominator? Both denominators together. This is the worst case. I mean, they don't have anything to do with each other really. So I'll copy in black what we originally had. And then we're going to put in purple the things we need. So what's missing in the first denominator? 1 minus cosine. So we multiply the bottom by 1 minus cosine, but right away, what else do we need to do? Multiply the top. Same idea over here. What's missing in this denominator? 1 plus cosine. But then right away we pay for it upstairs. Okay, we're going to merge them together into one massive fraction. The new denominator is just either of these denominators that we had. Let's go ahead and distribute here. What do we get when we FOIL on the bottom? Right, that's that pattern where the outers and inners cancel when you FOIL. Okay, upstairs we have the thing in purple plus the other thing in purple. Let's merge them together. Yeah, it's just 2. You guys see that? We're doing 1 plus the 1 minus cosine plus cosine. Cosines cancel, so we just get 2. And for the first time, I'm feeling optimistic in the middle of doing this problem. What has the goal been all along? Yeah, this is what I want. I started with the left-hand side, doing a lot of work to transform it. Ultimately, it needs to get to 2 cosecant squared. I say don't ever cross over, this line right here, but you can sneak a peek every once in a while to kind of guide you. That's what we're after. And for the first time, I'm feeling better because I see my 2. That 2 that I found in the numerator actually is that 2 that we're after here. So somehow this 1 minus cosine squared on the bottom is really a cosecant squared. Okay, there is an identity that we have seen before. Maybe we didn't use that word, but You guys maybe have seen this a couple of times. If you take sine squared of an angle plus cosine squared of that angle, what do you always get? That's always 1. I will say this is one of the most important identities that you guys are going to use. Sine squared plus cosine squared is 1. And the reason that identity came to mind was I saw cosine squared down here in the denominator. And so I feel like I can build a 1 minus cosine squared up here. Subtract the cosine squareds from both sides. And what do you get on the left? Sine squared. Everybody see it? Sine squared is 1 minus cosine squared. So I'm going to copy my 2. And on the bottom, what is it really? It's really sine squared. Everybody see it? And then we're there. Because sine squared on the bottom is really what? Cosecant squared. In fact, I think we knew that because isn't that what we had to type in? I had to type in a 1 over sine squared. Okay. So this is equal to 2 cosecant squared x. And I'll just put the last little piece here. Since 1 over sine is cosecant. Questions on that? Okay, an observation about identities. We'll do one more together, and then you guys will do a bunch of practice on in your groups. So one observation is that oftentimes there's more than one way to prove an identity. We followed a particular path here. In the next example that we do together, I'll show you a couple of different ways to get to the answer. Some students like that. They see the freedom, the flexibility involved there. Other students would prefer if there were just one concrete process that you could follow every time. There just isn't one for proving every identity in the world. So I'll give you some general pointers, and then it's going to be a matter of playing around. And that can be frustrating for some because you can do some stuff and then get to a dead end. And a lot of math problems that we do in class, they don't have a dead end. If you just follow the step-by-step process, you'll get there. But here, there's not a linear path every time, or at least it's not clear what it is all the time. Okay, let's take a look at 4. Here are some important identities. So we've seen a few identities already. We used a couple of them here. For example, we know that sine squared plus cosine squared is 1. That's an important one. We use another one over here. Cosecant is the same as 1 over sine, right? That's an identity. You guys know that tangent is what over what? Sine over cosine. That's another identity. So you guys already have a handful of these things. Turns out there are more than you could care to memorize out there. We're not going to look at too many, but here's a big old collection. The first ones are called the double angle identities. You see why they're called the double angle identities? Because the right-hand side involves like a theta and a theta, but the left-hand side involves 2 theta. So somehow, if you have information about the theta, you can then get information about the double angle. So if you know what the sine of 22 degrees is, you can figure out what the sine of 44 degrees is using that first identity. Okay, then you have these symmetry identities. Have we talked about these? I feel like we might have seen these on one of the reference sheets. Did we not do like even odd stuff for sine and cosine? I don't remember. Anyway, so here are some identities that tell you how the negative of an angle is related to the angle itself. And then down here, translation identities. You guys know translation just means moving left, right, up, down. This is how you can translate and figure out what cosine has to do with sine. All right. So in terms of so I'm just throwing like a lot of identities at you at one time. We're going to prove a bunch of these. Other ones I'm going to ask you guys to think about. Let's start with number 5 on the next page. Vance? Okay, so that is not supposed to look familiar to you. We just saw it on the previous page for the first time. But if we believe that one, and I'm going to convince you that that one is true next class, but if you take my word for it for right now, then we can get to some other identities relatively cheaply, I'll say. So let's use that identity right there. Cosine squared minus sine squared is equal to cosine of 2 theta. Pretend that we believe that to be true at the moment. Let's get another way to figure out what cosine 2 theta is. So I'm going to assume that it's cosine squared minus sine squared. But didn't we just a minute ago have something that told me what sine squared of theta was equal to? In the previous identity, what was sine squared? Was a 1 minus cosine squared? Like we used that just a minute ago. So how about instead of this sine squared right here, we put 1 minus cosine squared? So copying that identity, the thing that we're temporarily believing, it's cosine squared theta minus, and then instead of sine squared, put the thing up above. 1 minus cosine squared. Everybody see the substitution we did? Okay, this is equal to, let's see, cosine squared theta minus 1 plus cosine squared theta. Distribute that minus sign. And if we combine, we get what? 2 cosine squared minus 1. Everybody see it? So what we just did is prove the cosine of 2 theta is the same as 2 cosine squared theta minus 1. And if you go back to the previous page, you'll see that in our big list of identities. Make sense?
Why is that useful?
It's useful because, all right, so let's take a look at, suppose we look at, I'm trying to think of an angle that we know double. Okay, let's do this. Suppose that you guys know, for example, cosine of 15 degrees, cosine of 30 degrees. How much is that? Yes. I think you're allowed to bring the first page of the packet, and you might find all of them on there. Yes? Yeah. How much is cosine of 30? Radical 3 over 2, that's on our unit circle. I can think of 30 as being double some angle. What is the angle? Is 15? Yes? So I can think of this as really being cosine of 2 times 15 degrees. All right. So that means that if I plug 15 degrees in here, then somehow 2 cosine squared of 15, subtract 1, is equal to cosine of 30. That's what that identity says. Okay, but I know what the cosine of 30 is. It's root 3 over 2. So if I do a tiny bit of algebra, I can then figure out exactly what the cosine of 15 is based on it, but it's not as simple as root 3 over 4. You have to, like, here's what you have to solve. Root 3 over 2 is equal to 2 times the cosine squared of 15. I don't know what that is yet. And then subtract the 1.
So that would have been really useful when you're working on it.
Yes. And you could build like and then once you know cosine of 15, you could then build cosine of 7.5 if you wanted to. So you could fill in a lot of stuff. Like the unit circle has only, I don't know, like 15 angles or something on it that are useful to us. Starting to use identities, you can build much more robust tables. Yeah. Okay, number 6. We'll go back to tacit A. Okay, so we'll just look at one of the symmetry identities. For example, sine of negative theta. Trying to figure out what sine of negative theta is. Okay, first of all, is the sine the x or the y? It's the y. Okay, so sine of theta is this number right here. And if I want to think about negative theta, in which quadrant is negative theta? If theta is in the first quadrant. The negative theta is just down here in the fourth. So just copy that angle down in the fourth. What do we notice about the x and the y down here? Same x, but the y is negative. Yes? So then the sine of negative theta is this length, but it's a negative number because we're below. And how does it relate? Well, it's just the opposite of the length up above. So sine of negative theta, is it the same as the sine of positive theta? No, it's the same, but it's the opposite sign. And that's using symmetry, which is why we call it a symmetry identity. You could do something similar for cosine and for tangent. They're all listed on the previous page and on the first page. Okay, and then translation identity coming down here. You guys see that sine and cosine look almost the same, right? You just have to pick one of them up and shift it a little bit to land it on the other one. All right, so suppose that we wanted to take cosine and land it on sine. If you wanted to take this point here and shift it over to that point there, how far do we have to move? There's a quarter of a rotation. In terms of pi, how much is that? It's half of pi. So I go pi over 2 to the right. So what does that mean? Let's see, cosine of t equals sine of t. It's not true right now, but if I shift the cosine and it can make it land on the sine. All right, so let's see, if I'm making it land, shifting cosine, I suppose that means I'm tweaking this equation. How do I make it shift to the right by pi over 2? So we do minus pi over 2, and that should land perfectly on the sine function. And that's one of the identities on the previous page. Okay, so we'll try 8, and then we'll do an example. Kate? Go ahead. Okay, so we've already used this one a couple of times today. Sine squared is 1 minus cosine squared. This sine 2x is a new one. We saw it earlier. I haven't proven it yet, but anyway, it's like, let's add it to our list of tricks, things that we can use. We'll go to B for Richard. Okay, so you don't need to read them, but every one of the 6 trig functions can be written with sines and or cosines. Yes? Here are there's sine and cosine, and then there's the other 4, and every one of them can be written with either sine or cosine, which is kind of nice because then you can get your equation with only sines and cosines instead of maybe some of these more exotic trig functions. All right, let's go to Emily for C. All right, and we kind of worked backwards a little bit on that first one that we did. Down here at the bottom, let's see, we were at this stage right here. I had a 1 minus cosine squared in the bottom. And then we kind of took a peek over here and said, well, we're trying to get to this cosecant squared. So maybe we're going to end up using this idea that cosecant is 1 over sine. So it's like, look at where you want to get and then sort of work backwards from there. And then we'll go to Sam, D. Okay, so we tried that. And then another technique that we'll see is factoring. This is not a complete list, just some ideas. And then F, Todd. All right, so, and I say that that's an important thing to keep in mind because again, this is not a linear process where if you just do these discrete steps, you'll always get to the answer. It could be that there are a lot of false starts, a lot of dead ends before you finally find a path as you kind of negotiate from start to finish. Okay, so we're going to do this one together, and then you guys will try some in your groups. 1 minus cosine theta over cosine theta equals tan squared theta over 1 plus secant theta. Somehow this is true for every single value of theta, and we're going to prove it. All right. First thing I'm going to do, I have to pick one of these two sides to start with. Again, you're never crossing over that equals sign. Okay, let's pick the left-hand side. I'm just going to write 1 minus cosine theta over cosine theta. What about secant? Going to multiply by secant? Like this? So I think what Garrett is saying is that cosine on the bottom is like a secant on top. Is that what you're saying?
Yeah.
Okay, so well, I don't know. I mean, so it's true. And Todd, what did you want to do? You wanted to flip the secant? So this secant Todd wants to put upstairs as a cosine. Oh my goodness. So I guess I can't write it that way. Cosine x. So is that true? Secant on the bottom is cosine on the top? The plus one is going to make it so we can't do that. Otherwise, it would be a great idea. Yeah, if you have a secant on the bottom, like here's something that's definitely true. 1 over secant is cosine. And absolutely, if I see a 1 over secant, I'm rewriting it as a cosine. But that 1 plus on the bottom makes it so we can't do that, unfortunately. Okay, so Garrett, do you like this idea, or you feel like it's not headed in the right direction?
I don't know. You said to get rid of scans. Get rid of that.
I see. Well, yeah. So I mean, so the next thing Garrett said after he made this observation was, well, it's not headed in the right direction. So you kind of have to look at where you're going. The difficulty with identities, I think, is that oftentimes there are so many choices that you have to pick from. It's sometimes hard to narrow it down. But if you kind of keep in the back of your mind the goal, then you might be able to cut off some of those dead ends before you get too far. Now, I don't want to say that that is a dead end, but I don't see it looking more like the right-hand side. Okay, so let's erase some stuff. Okay, so here's one thing we could do. Do you guys believe that I could take this and make, yeah, Chris? We can make two fractions, just 1 over cosine minus cosine over cosine. Is that true? Okay. And I'm not saying that necessarily looks more like the answer, but at the very least, this involves a -1, which is simpler than anything I've got so far. 1 over cosine is better known as what? Secant. Okay. Secant theta -1. I don't see that it's the same as the answer. Shouldn't be obvious that it's the same as the answer. And I don't even see how to get from here to the answer. But I would contend that this is at least as simple as the one that we started with, and maybe simpler than the one that we started with. So perhaps it's progress. And if you get to a place where it's just like, I don't know where to go from here, there isn't anything natural to do with secant theta -1, well, you can start with the other guy. Tan squared over 1 plus secant theta. And I want to make sure you recognize I'm not breaking my fundamental law, which is never cross over the equals. At no point am I going to add 7 to both sides. I don't have a both sides. But what I could do is just manipulate this red expression. And if eventually I can get it to look exactly like secant theta -1, do you see that we're done? Like you have these two things that you're hoping are equal. You simplify one and it gets down here. You simplify the other. If it gets to the same place, well, they must have been equal from the beginning, right? So let's see if we can do something with this. Maybe head towards that secant theta -1. Okay, I see a tan squared. You guys remember when we saw sine squared? We had some identity that we used, the sine squared plus cosine squared is 1. Well, there's another identity with a tan squared in it, and maybe it's not as familiar to us yet. But if we go to the very first page, then we will see that it is missing. So let's put it in. All right. Here's another identity. We can put it right next to this Pythagorean identity. it's as follows. It says tan squared t plus 1 equals secant squared t. What's that? Yes. Yeah, that's a good technique. I'm going to write down one more that goes hand in hand. There's like 3 of them that kind of work together. The last one is a 1 plus cotan squared equals cosecant squared. Right. All right, so write those right on the first page so that you have them when you bring that with you to the quiz. And I'll say again, we have something with a tan squared in it. I'm thinking that identity. It's the only one on the page with a tan squared in it. So, well, actually, it's probably not. But it's the only one we know right now with the tan squared in it. So what is tan squared equal to? Well, I can bring that minus 1. I can bring the 1 over by subtracting 1. So let's do that from both sides. And we are here. And so I'll just write down that one that we're going to play with again. It was tan squared theta plus 1 is secant squared, which means that tan squared is really secant squared minus 1. Okay, so instead of tan squared on the top, what are we putting? Secant squared minus 1. So this red thing on the blue or the red? Yeah, that's fine. Yeah, that's perfect. I'm going to do something that's equivalent, but it looks a tiny bit different. What do we do here? Secant squared minus 1. That's what we have on top. Okay, and I really like that one because that one has only secants in it, and the blue thing at the bottom has only secant in it. And I think we're just about done. We can factor this thing on the top, can't we? Secant squared minus 1 is really 2 parentheses. What goes in? And then what happens? We cancel. 1 plus secant on the bottom is the same as secant plus 1. So all that's left is secant theta minus 1. Why is that a good thing? Okay. Chris? This? I think so. One step fewer. Todd's way is easier. So I'll just write it and then erase it so it doesn't get too cluttered. But I think, where were you, Todd? Right up. Yep. What did you do? 1 plus secant on top. But not 1 plus, 1 minus. When you say both sides, do you mean here and here? Okay, so make sure we don't go across because we don't have an equals to play with, so you can't do both sides. But what I was thinking you were saying was you'd multiply top and bottom here by 1 minus secant, just playing around with the one expression here. Well, it's not that you got lucky, it's but you're going across the equal sign, which you're not allowed to do with identities. But what you could do is recognize that the bottom here is, let's see, so this is a n squared, 1 minus secant, 1 plus secant. What is this on the bottom? Oh, I see. Yeah, we can't do that. Okay, so let's go back to there. All right, so ultimately what happened is we played around with the left-hand side and we played around with the right-hand side, completely separate. It turns out both of them turn out to be equal to secant theta minus 1. So they must have been equal to each other at the start.
This seems like the kind of thing where if you don't already know like one of the identities, you need to solve the problem, you can spend an hour working on it, so you'll never get there.
Yeah, so in terms of my expectations, like I will give you an identity and say prove it, or I'll give you something and ask you to say, show me it's not an identity. I think you're talking about the discoverer's side of things, like how do you prove one of these things if you don't know what the other side of the equation is? Well, the good news is if you just, I don't know, somehow randomly decided you were going to start with that thing circled, you can go wherever you want. Going from here to here, that's an identity. Going from there to there, it's an identity. Like wherever you stop, you found some identity.
Right.
There's no destination. At some point, somebody figured out that you could kind of keep going if you decide to eventually make your way up here. And so that's how they came up with that. But, you know.
I guess there is a destination of getting
Somewhere useful, yeah. Yeah. Okay. So that's one way to go about doing identities is to play with each side separately and get them to both be the same. Another idea would be to somehow start with the left-hand side and make your way eventually to the right-hand side, never really playing with the right-hand side. That's what we did on the first one. Okay, so this is good. I said I might do it in a second way, but I don't think I will. I think that this is fine. It illustrates some of the ideas. Play with both sides, never cross the equals, rewrite using identities, and eventually, hopefully, we get to two things that are the same. So we have 26 minutes, 27. There are a bunch of identities for you guys to try down here at the bottom. So what you're going to do is you're going to decide whether it's an identity by graphing both sides. And if it is, then you're going to prove it. If it's not, and you're really hoping it's not, because if it's not, it's so much easier for you. All you have to do is find me a value of x that shows that they're not equal. Okay? So talk with each other, and I'll walk around.